All right, the classic thin film situation, the one that we always refer to, I think it was the first graphic I put in the note that's posted for the online learners, a soap bubble held in air. We usually picture a soap bubble as round, but for the scale that we're talking about, these in the order of nanometers, I'm going to just approximate the soap bubble to be rectangular. It's most likely curved, but we can approximate it to be rectangular. The index of the soap is 1.3. It's got air on one side and air on the other side. It's symmetrical, it doesn't really matter which way I draw it, but just because I'm going to draw the light coming from left to right. Bundle of light number 1 travels through the air and bounces off the film. That's bundle of light number 1. Bundle of light number 2, it's weird to think of it this way, but it travels into the soap, and when it gets to that second interface, that second boundary, some of the light would keep going, but for the thin film reflection, I'm concerned about the light that reflected off of the air. We don't usually think about reflecting off of air, but it's an effect that happens if you've got light in a medium. When it hits that medium to air interface, some of the light will reflect backward. So I don't forget, I'm going to get the lambda prime right off the bat. Lambda prime is the lambda in air. In this case, it was 390. Divided by the index of the film. In this case, the film was soap with an index of 1.3. 39 divided by 13, or 390 divided by 1.3 is 4. In this case, 100. Now, the next step is to look at the reflections. If we look at this one, the ends are all out of whack. They go from small to big back to small. Since the ends are out of whack, really what that means is bundle of light number 1 reflects off a larger end, but bundle of light number 2 does something different. It's in the 1.3 and reflects off of air, so it reflects off a smaller end. Because they go through different things, it's kind of like one bounced off a free end, one bounced off a loose end in the Slinky lab. We don't even need to know which one changed phase and which one doesn't. The bottom line is they went through different things. Because they went through different things, one reflected off larger, one reflected off smaller. If we just focused on the reflecting, they're out of phase with each other. Now the logic step. Because of the reflecting, they're out of phase with each other, but the question says there's to be a bright reflection. The question wants there to be constructive interference. If they're out of phase, we need to get them back in phase. So we need the 2t to be half of the lambda prime. It's kind of like a double negative. Half a lambda prime is usually an out of phase thing. The reflecting is another out of phase thing, so out of phase twice puts them back in phase. Or if we flip the 2 over, we need the thickness to be a quarter of the lambda prime. For this one, the lambda prime was 400, so the thickness is 100 nanometers. What you can't do is look at a question and say, oh, this question says bright. Bright means in phase, so the extra distance must be a lambda prime. You have to consider both what the question asks for, in this case bright or constructive, and you have to consider the order of the ends. And those two together will match the question. One that I didn't type up but might be worth looking at or thinking about, if you've ever put like a low quality screen protector on your phone or tablet, sometimes an air bubble trapped between the screen protector and the screen, sometimes that little pocket of air acts like a thin film. So maybe you might have a screen protector with a bubble of air, and when you look at that bubble of air, it looks kind of rainbowish. That's a thin film effect coming from the air wedged between those two chunks of plastic and glass, acting like a thin film. Think about